Hi students. Today I am Mohan Raj, Assistant Professor, Electronics and Communication Engineering, K.S. Rangasamy College of Technology. Today we are going to discuss about Okumura model in mobile telecommunications and networking. So what is meant by Okumura model and its applications and where it can be used. So first Okumura model. This is one of the most widely used model for signal prediction in urban areas. So in all it can be urban areas and classified the network can be classified in urban areas and rural areas. So and most widely used models for signal prediction. So in urban areas there is more crowd and density is higher than rural areas. So while applicable it can be Okumura model, it can be applicable for signal prediction in urban areas. This model is applicable for frequencies in range that is 150 megahertz to 1920 megahertz. So although it is typically extrapolated up to 3000 megahertz and distances of 1 kilometer to 100 kilometer. So it can be applicable to wide range of frequencies and also to the wide range of distances, and it can be used for base station antenna heights that ranging from 30 meter to 1000 meter. So this is applicable for Okumura model techniques. And next one, Okumura developed a set of curves giving the median attenuation relative to free space, so that is AMU, in an urban area over a quasi smooth terrain with a base station effective antenna height, so that is HTE of 200 meter, and a mobile antenna height, that is HRE of 3 meter. So these various curves can be calculated in different regions, so in terrain regions and also urban area and rural area. He can develop a set of curves for calculating the median attenuation. So these curves were developed from extensive measurement using vertical omnidirectional antennas at both the base and mobile, and are plotted as function of frequency in range that is 100 megahertz to 1920 megahertz, and as a function of distance from the base station in range that is 1 kilometer to 100 kilometer. So this curve can be measured with the frequency range that is 100 megahertz to 1920 megahertz, and also it covers the base station distance from 1 kilometer to 100 kilometer distance. And another one important consideration is there is omnidirectional antennas. So omnidirectional antennas, which means it can cover in all the directions. And next one, to determine path loss using Okumura's model, the by using this formula we can determining the path loss. The free space path loss between these points of interest is first determined, and the value of AMU as read from the curves is added to it along with the correction factors to account for the types of terrain. The model can be expressed as that is L50 in decibels equal to LF plus AMU minus GHTE minus GHRE minus GAREA. So this is the formula to determining the path loss by using the Okumura's model in terrain region. So where L50 is the 50th percentile median value of propagation path loss, and LF is the free space propagation loss, and AMU is median attenuation relative to free space, and GHTE is the base station antenna height gain factor, and GHRE is the mobile antenna height gain factor, and GAREA is the gain due to the type of environment. So this is the formula for obtaining the path loss. And note that the antenna height gains are strictly a function of height and have note that the antenna height gains are strictly a function of height and have nothing to do with the antenna patterns. So in Okumura model, the plots of AMU, FD and GA or EA for wide range of frequencies are shown in the figure. Furthermore, Okumura model found that GHTE, so GHTE means that is a base station antenna height, and GHRE means antenna mobile antenna height. And furthermore, the Okumura model, so after the calculations and seeing the curves, the Okumura model found that the GHTE varies at a rate of 20 decibels per decade. And GHRE, so GHRE is, that is a mobile distance, that is varies at the rate of 10 decibels per decade for height less than 3 meter. So this is the calculations obtained by using the Okumura path loss gain formula. And also this is the formula for detecting the path loss also. And GHR equal to 20 log HTE divided by 200, so which is the distance measured from 1000. So by measuring the various distances, the GHRE can be obtained. So but for the distance of 100 meter, 1000 meter to 30 meter, so the formula can be obtained, that is 20 log HTE divided by 200, and for that is less than or equal to 3 meter, so the obtaining formula is 10 log HRE divided by 3, and the distance obtained from 10 meter to 3 meter of the height, so we can obtaining GHRE equal to 20 log HRE divided by 3. So this is the formula for determining GHTE. And in median attenuation relative to free space over quasi-smooth terrain, so this is the graph obtained for various frequencies. So on median attenuation, so by measuring the frequencies, that is ranging from 100 to 3000 megahertz, so obtaining the median antenna frequencies, that is in urban area, it can be increasing in the urban area. So various the median attenuation can be increased in terms of kilometers. So while increasing the kilometers, the frequency can be increased. So the mean attenuation can be calculated based on the frequency and distance measured from the base station and the mobile base antenna. An Okumura model is wholly based on measured data and does not provide any analytical explanation. So this is one of the disadvantages, and for many situations extrapolations of the derived curves can be made to obtain the values outside the measurement range, although the validity of such extrapolations depends on the circumstances and the smoothness of the curve in the question. An Okumura model is considered to be among simplest and best in terms of accuracy in path loss prediction for mature cellular and land mobile radio systems in cleavated environments. It is very practical and has become a standard for system planning in modern land mobile radio systems in Japan. So another the major disadvantages with the model is its slow response to rapid changes in the terrain. Therefore, the model is fairly good in urban and suburban areas, and in terrain region it is difficult to determine the path loss, and therefore it is good used in urban and suburban areas, and also it is not as good in the rural areas. And common standard deviations between predicted and measured path loss values are around 10 dB to 15 dB. So this is the calculated path loss values in urban and suburban region. So predicted and measured value. So that ranges from 10 decibels to 15 decibels. And this is correction factor GA or EA for different types of terrain. So the path loss can be determined in different types of area, different types of terrain region. So first in open area, so in open area the correction factor that is around 22.5, so like that. So by varying the frequency from 100 to 3000 megahertz. And in quasi open area, so it is slightly decreased from open area compared to, so there is around 17.5 like that. And in suburban areas it is well good in, that is a 5, so correction factor that is 5 decibels when the frequency is increased from 100 to 3000 megahertz. So this is the path loss by Okumura model. We can determining the path loss of the which is best suitable for urban and suburban areas, and that is not best suitable for the terrain and rural areas. So by using this attenuation formula, Okumura's model, we can obtaining the path loss for urban and suburban areas. Thank you.